All right, everyone, and welcome to the first of 5 videos for this section. Don't worry, the first 2 are going to be kind of long. The last 3 should be pretty short, although I'm saying this at a time when you can tell how long the videos are going to be, and I cannot. Hope you can recognize me as well. Anyway, we're going to be talking about 3 things in this first video, but they're all very, very closely tied together. All right. Before we do that, I'm just going to go into some definitions. All right. So these definitions are all going to be very, very similar, and I think you will probably not be too surprised what they are after the first one. Okay, so all of these are just different ways. The whole point of this section, composition of functions, is different ways that we can combine functions. And there are many uses of combining functions, and essentially we'll see some of them at the 5th video at the very end with some applications. But suffice it to say that essentially right now, what we just care about is, can we combine different functions? So we can combine 2 functions f and g into f plus g, and all that is just adding the functions together. Similarly, f minus g, all that is subtracting the functions. F times g, all that is multiplying the functions, and believe it or not, f divided by g is just dividing the functions. Okay, so this is essentially shorthand for various ways that we can combine these with algebraic operators, plus, minus, multiplication, division. Okay, so let's actually compute some of these things. All right, example 1. This microphone like right in my face. I can't see anything. I can only see the microphone, so I'm just writing blind. Wish me luck. Example 1, find the following. For f of x equals x minus 1 and g of x is equal to x squared minus 1. Right? So part A, I want you to find out what f plus g of 2 is. The definitions, right, had x's in them, but you can replace the x's with 2's, no problem. So all this is with the definition is f of 2 plus g of 2. We just find out what each of these function values are and add them together. So f of 2, just replace x with 2. We get 2 minus 1. Plus g of 2, just replace x with 2. 2 squared minus 1. Well, that's going to be 1 plus 3. Or 4. And that's function operators in action. Okay, and we can do more of these just to really show what's going on. For example, we could do something a little sillier. F plus f of 2. In the definition, these don't have to be different functions. It could be g plus g of 2, f plus f plus f plus f plus f of 2. Right? It can be anything, but the definition still holds. It's going to be the first thing evaluated at 2 plus the second thing evaluated at 2. So it's just f of 2 twice. So again, f of 2, just like before, is still 1. So it's just 1 plus 1 or 2. All right. So don't be confused if in this section you see the same function twice. Just instead of g over here, it's just going to be whatever is in that second spot. All right. Well, let's do some more. Let's see. What about find f minus g? And again, just like sometimes we say f, sometimes we say f of x. It's similar here. Sometimes we say f minus g, but what we really want to know is what is f minus g of x? Okay, so the book kind of does this, so watch out for that. Again, just using the definition, that's going to be f of x minus g of x. And then f of x is something that's on the previous side of my paper. X minus 1 is f, and x squared minus 1 was g. So f of x, just replace it. Is it really x squared minus? Yeah, it is. Minus g. Now be very careful here. We need to subtract the entirety of g, x squared minus 1. The whole thing is getting subtracted. So you need parentheses here. Okay. It's going to be x minus 1 minus x squared plus 1. Very careful with those. Now we just simplify. We have a minus 1 and a plus 1. Those cancel out. We're just left with x minus x squared. That is f minus g of x. All right, last one. F divided by g. So again, this is really just f divided by g of x that we want. Using that definition, that's going to be f of x divided by g of x. And again, what is f of x? F of x is x minus 1. What is g of x? G of x is just x squared minus 1. Now, for all you algebraic superstars, you might say, aha, we can factor this and cancel, right? That works with expressions, but it doesn't really work with functions, because when we cancel, we change the domain. We'll get into domain later. So later on, I'm going to show you why we can't cancel right here. But well, we can cancel. It just depends on how you want to treat it. Short answer is leave it like this. Okay? Unless you specify the domain, you're not going to be able to cancel. Anyway, that's the first part of the video, and we're already 6 minutes in. Again, these first 2 videos are going to be longer than normal, but the other 3 should be shorter. This is part 1 of video 1. Next, we need to talk about intersections, okay? Specifically, intersections of sets. So if I look at the intersection between 2 sets, really what I want to know is, what do these sets have in common? Right, that's what we mean when we say function set intersection. So let's look at some examples. Example 2. Find the following. The interval 2 to infinity intersected with the interval negative infinity to 5. It's supposed to be a bracket. All right, and again, that's our sign for intersection. It's a big arc. Arch intersection. Okay, so one way that can be useful to find intersection of sets is draw them on the number line. Okay, so I have a number line over here, and let's say we have something 2 to infinity. Looks like that. Then we have another number line, 5. 5 is bigger than 2, so let's write it over here. 5 is the biggest this second one can be. Goes all the way off to negative infinity. Okay, and hold on, we have some cat interference. Hello. So we just need to see, what do these 2 things have in common? So again, they don't share anything over here. Whoop, here they share stuff, here they share stuff, here they share stuff, and they don't share anything over here. Okay, so the intersection, maybe this is not putting a line between number lines. The intersection is just starts at 2 and goes up to 5. And that's the intersection of these sets. So we'd say their intersection is a set from 2 to 5, like so. And number lines can be helpful. You don't need the number lines. They really can be helpful to show what's going on here. All right, that's our answer for part A. All the numbers that are in common between these 2 sets. Do another one. Part B, the intersections of sets 0 to infinity and 2 to infinity. Oh my word, this is what happens when I'm not looking at my paper. I've just written over the same thing that we had just talked about. Well, that's replaced now. Okay, so we can do the same thing with number lines. Got 0 to infinity. Let's say that looks like this. We have, that's supposed to be 2 to infinity, okay? So 2 is over here, 2 to infinity. We just have to see everything they have in common. So nothing in common here, nothing in common here, still nothing in common. And finally, they both are shaded. Okay? Since they're both shaded here, in fact, they're actually both shaded everywhere, 2 or bigger. That's going to be our answer here. Interval from 2 to infinity. All right, let's do one more. The set of all x, we're going to use set builder notation here, such that x is not equal to 1, is going to be intersected with the set of all x such that x is greater than or equal to 0. We can solve this the same way. Let's get a number line. And number line here. The first one is everything except for 1. That's everything less than 1 and everything bigger than 1. The second one is just everything bigger than or equal to 0. Looks like this. So then their intersection, again, they don't share anything, they don't share anything. Oh, they share stuff here, and then they don't share that point, and then they share everything else after that. The intersection will start at 0. We'll skip 1, and then go off to infinity. The intersection looks like this. So a couple of ways you could phrase this. I'll answer with interval notation, 0 to 1, union 1 to infinity. As a side note, notice that the intersection is just the upside down union. Okay, because union is what is in either, and intersection is what is in both. So they're very related concepts, right? That's how we can do intersections. That's the second part of the video. Now the third part of the video is domains of algebraic operations. Okay, the short answer is, if you're good with the first 2 parts, you're probably going to be good with the last part. Important? No, it's not important. We're good to go. We use the backside of whatever I was using this paper for. So, property. The domain of f plus g, I got some good news for you. F minus g and fg are all the same. These 3 functions all have the same domain. That's kind of nice. You might say, oh, there's a 4th function that you're not mentioning. We'll get to that later. Is the intersection of the domains of f and g. So find the domain of f, find the domain of g, find their intersection, and that intersection will be the domain of these 3 functions. Okay? And similarly, for f divided by g, find the intersection of their domains. And then we got another intersection. So then intersect, ooh, that's totally a T. Then intersect with the set of all x such that g of x is not equal to 0. So find the intersection of the domains of f and g, and then combine that, because we can't divide by 0. So everywhere where g is equal to 0 needs to be a part of that domain as well. You can really see some ghost math in the back here. We got a function turning x to a big box and outputs y's. Hopefully it's still clear enough to read, and my reusing of paper does not punish your educational experience. All right, so let's use this. Example 3. For f of x equals the square root of x plus 1, and g of x equals x minus 1, find the domains of the following. Part A, f plus g. As a side note, notice that we don't actually have to find the domain, or sorry, we don't actually have to find what f plus g is, right? To find the domain, just have to find the domains of them individually. We don't actually need to calculate f plus g, okay? So, first, domain of f. That's the domain of the square root function. Remember, that's when the inside is greater than or equal to 0. Or when x is greater than or equal to -1, you can subtract 1 from both sides. Okay? So if you want, you could write this in interval notation. You don't technically have to yet, but we'll get -1 to infinity. Now we find the domain of g. Well, this is just a line, linear function. Domain of g is all real numbers. So what does everything have in common with this interval? It will just be that interval. And again, if you really want to see it, we have the number line, -1, off to infinity. What does this number line have to do with everything? Where do they overlap? Well, this is everything. So they will just overlap at that first thing. Okay. So our answer is their intersection, the intersection of these two sets. And the intersection of those two sets, so -1 to infinity, intersected with the set of all real numbers, is just -1 to infinity. And that's our answer here. Now is the part you're really going to like. Okay. Part B. What's the domain of f minus g? We already found it, right? The domain of these three functions is all the same. It's just the intersection of the individual domains, which we just calculated. So the domain of this is also going to be -1 to infinity. Part C, what's the domain of f times g? Well, we already found it twice. It's also going to be -1 to infinity. Now part D is a little different. What is the domain of f divided by g? So we already found the intersection of their domains, right? That's the intersection of their domains. We just have to intersect this result with when is g equal to 0. We need to find the set of all x such that g of x equals 0. Technically not equal to 0. Very different. When is something equal and when is something not equal is like literally opposites. Anyway, so that's what we need to find. Find this, intersect it with that previous set that we've got. Okay, so when is g of x equal to 0? When is g of x not equal to 0? Well, g of x is just x minus 1. So that's when x minus 1 is not equal to 0. Well, add 1 to both sides, that's when x is not equal to +1. So we need to take the intersection of these two sets, -1 to infinity, and the set of all x, such that x is not equal to +1. Well, this first set, -1 to infinity, looks like this. The second set is everything except for +1. So everything less than +1 and everything greater than +1. And so what do these sets have in common? Well, they have in common stuff starting with -1, and then all the way up to +1, but not actually hitting it. Union +1 to infinity. Okay? And that's the intersection of this quotient function f over g. All right, that's the longest video, 18 minutes long. Next one will be still long, but shorter, and the last three should be a little nicer. All right, if you have questions, you can ask me, and go ahead and get started.